Okay, folks. Right, this week's lesson is going to be on forces, so I thought I'd make a little video. Some people can find forces quite confusing, so hopefully this video helps. So when you first open up, you will see this. So we're going to learn about forces, and your success criteria would be you should be able to state Newton's first, second, and third law and give real life examples. And you should also, we're going to be going through 2 or 3 equations that you should be able to use and solve problems with, all using forces. I've put the PowerPoints in there for you. You can look through them or you could just listen to this video. It's just going to be just as good, he said. Right, so first step, last week we did acceleration and velocity time graphs. So I'd just like you to work through these 3 starter questions just to try and consolidate our learning from last week. It should all be using the acceleration equation, A equals V minus U over T. Once you've done those 3 questions, task 1 is read the PowerPoints, listen to this video. Please take notes in your jotter. There's going to be things that you don't know. It's not all going to be recap from S3. There's going to be some new processes in there, so take notes in your jotter as you go along. And once you've done that, submit this assignment so Miss Murray and I know that you've read, listened, understood, and noted facts in your jaw, and then you can move on to the tutorial questions plus the past papers afterwards. So I'm just going to go over some facts about forces. So we did do forces in S2 and S3. So if you look in the files section, you will find the dynamics booklet, the recap from S3 you will find in pages 14 and 15. You can read over that yourself, it's in the files section. Right, Newton's laws. Right, forces, when they act on something, they can change the shape of an object. So I'll put a little picture in here of an elastic band. The elastic band will stay the same shape until you start to pull it apart. So you're changing the shape by stretching it. Likewise, say an empty can of Coke will stay that same shape until a force acts on it. So you crushing a can, you're putting a force on that can, so you're changing its shape. So we've covered that one. Forces can also change the speed of an object. So this little car here, if it's travelling in this direction, if you put your foot on the accelerator, the speed is obviously going to go up, so the speed is changing. If you put your foot on the brake, the velocity is going to go down. So the speed of that car is being changed by forces in that way. And the third one is the direction of an object can be changed if you have an active force on it. So that might be if you're traveling in that direction and a car hits you from the side, you're no longer going to be going in that direction. You're going to probably go in that direction. Likewise, if you're walking along the road and someone pushes you from the side, you are naturally going to change direction because a force is acting on you. So force is always measured in newtons, and we've got a couple of equations coming up soon where we will be able to use that. I just wanted to talk about friction first though. Friction is quite an important force. Again, when you're driving a car, let's say you're driving in that direction, you have your driving force going in that direction. Downward, you're going to have the weight. And remember, weight depends on the mass of the car and gravity. So that's all going in a downward direction. If you have the road here, there is naturally friction between the road and the tyres, and that's why tyres wear away, because there's friction, there's kinetic energy changing into heat, so there's friction between the tyres and the road. There's also friction between the brake pads and the wheels when they close so you can brake. Another force on a car is in the opposite direction. So as you're driving in that direction, you've also got air resistance acting. If you've ever stuck your head out the window while you're driving, you can feel the wind or the air on your face. That's air resistance. That's a force acting in the opposite direction of the driving force. So those are some of the forces acting on a car. So now I want to move on to Newton's first law. So Newton's first law states that an object will stay at rest, so it won't move, or it will stay in motion at a constant velocity in the same direction until acted upon by an unbalanced force. So let's look at a couple of examples here. So this stone here, this is totally balanced, a balanced force. It stays at rest. There's no forces acting on it. Well, I say there is forces acting on it because there's a weight pointing down the way, and there's also, if that's lying on the ground, there's also a force acting upward from the ground onto the rock, but those two forces are equal and balanced, so therefore the rock does not move. Next example, that same rock, but we have two men pushing inward, and let's say they are both pushing inward with a force of 50 newtons. That force is equal, totally balanced, so again the rock will not move. Third example, so one of the men has moved over to the other side, and so instead of 50 in the opposite direction, they're now pushing with 100 newtons in that direction. So the rock is naturally going to go in that direction because there is now an unbalanced force. It is no longer balanced. Next example, a football on the ground at rest. Again, its weight pointing down and the force from the ground onto the ball are balanced. It will stay at rest. Next, someone comes along and kicks that ball, so they are acting a force upon it. It is therefore now unbalanced because it's had a force from that direction. The football is going to go in that direction. That football will stay in motion until another force acts on it. So I know there's air resistance going in that direction. Gravity is also pulling it down. But let's say in theory, if there was no air resistance or gravity, that football, let's say it was in space, that football will continue at a constant velocity until it's acted upon by a force. And then in the last diagram, the force is the ball hitting the net. So therefore, there's a force acting on it. Its speed and direction is naturally going to change. So I think that covers Newton's first law. Newton's second law, it describes how an object will accelerate if there is an unbalanced force on it, and that's using this equation: force equals mass times acceleration. For those that like the triangle, which Miss Murray will kill me for putting this in. Force, mass, acceleration. Force, like I said, is always measured in newtons. Mass is in kilograms. So they will try and trick you in exams. They might give you a ball weighs 500 grams. You've got to calculate the force on that. Remember and change that to kilograms by dividing by 1,000. 0.5 kilograms. Right, that can be used for regular stuff in motion. When we think about gravity, it does get a little bit more tricky, but we should have done this in third year, so I will go over it again very briefly. You can see the similarities in these two equations because F and W are both measured in newtons. They both have mass in them, which is in kilograms, and acceleration is meters per second squared. And gravity is also, in theory, an acceleration, 9.8 on Earth. But another unit symbol for gravity is Newton per kilogram, because gravity equals weight over mass, which is Newton over kilogram, so it's Newton per kilogram. I hope that makes sense. So there's a lot of similarities between those two equations. I just wanted to recap the difference between mass and weight before we go on. So we have this person here. Let's say this person has a mass of 80 kilograms. Mass does not change. It's the amount of matter in an object. This person weighs 80 kilograms on Earth. That person went to Mars. They would still weigh 80 kilograms. Their mass does not change. It's their weight that changes. So if you were given a question, calculate the weight of this person on Earth, you would do weight equals mg. They weigh 80, and you have to calculate their weight on Mars. That would be the same. 80 times g, and therefore you would need to go to your data sheet. So gravitational field strength on the Earth is 9.8, Mars is 3.7. So it's 80 times 9.8, and that will give you your answer, whatever it is in newtons. And on Mars, the gravity is 3.7. You see your weight is a lot lower on Mars because the gravity is a lot lower, nearly a third lower. So that recaps mass and weight. Now let's talk about resultant forces. Let's say we have a box here. 30 newtons pointing to the left, 30 newtons pointing to the right. The resultant force is 0 newtons, so it's not going to move, it's going to stay at rest. The second one, 30 newtons to the right, but 50 newtons to the left, so the resultant force is going to be 50 take away 30. So 20 newtons. And remember, force is a vector, so you also need to give it a direction. So if the question gave you a compass, you would say 20 newtons to the west. If it didn't give you a compass, then 20 newtons to the left is sufficient. Right, last couple of things. Free fall, wanted to talk about something called terminal velocity, and that's quite important. So let's say you have an object in your hand, this ball. That ball is going to fall vertically because of gravity. So it starts off as the initial velocity is 0 because you're holding it. So you let that go, gravity is going to naturally pull that down to the ground at 9.8 meters per second every second. That object will continue to accelerate until the force acting downward, so the weight, and the force acting upward, so the air resistance, are balanced. When those two are balanced, it will start to fall at a constant vertical velocity, and that constant vertical velocity is known as the terminal velocity. Now, it's unlikely a ball, if you're only dropping a ball from a short distance away, it's unlikely it'll get to that terminal velocity. So the best example I can give you is a free fall diver there. Jumps out an aeroplane at possibly, what do they jump out at? 10,000 meters. Gravity is naturally pulling him down. when the gravity pulling him down and the air resistance or the drag becomes equal, he will now travel downward at constant velocity. And that constant terminal, that is your terminal velocity. I hope that makes sense. I just wanted to give you a little tester question in here. Let's go back to this dropping this ball. Let's say I drop this ball from 3 meters high. The ball has a mass of 0.5 kilogram, and the time it took, I maybe used a stopwatch. I done it 3 times, took an average. The average time that I got was 0.8 seconds, and it started off at obviously rest 0 meters per second. I want to try and calculate its speed just before it hit the ground. There's 2 ways you can do this. I'm going to show you both ways. Right, as you're holding this ball, it has potential energy. And when you let it go, all that potential energy is going to change to kinetic energy. So the potential energy it has before you let it go, remember this equation, EP equals mgh, 0.5. Gravity, we're on Earth, let's assume we're on Earth, 9.8, and its height is 3 meters. So 0.5 times 9.8 times 3 meters high, 14.7 joules. That's its potential energy. That potential energy is now going to change to kinetic energy. You should all know the equation for kinetic energy from your sheet. EK equals 1/2 mv squared. And now we want to calculate the speed. We want to know the speed that got to as it dropped from that height. So I'm just going to rearrange for V. So times both sides by 2, so it's 2ek. That gets rid of the 1/2, which is mv squared. Move over the m, so v squared equals 2ek over m. Square root both sides, so v equals the square root of 2ek over m. Let's plug in our numbers. The square root of 2 times the energy, which was 14.7, all divided by m, the mass, which was 0.5 kilograms. Let me do that quickly. 2 times 14.7 divided by 0.5, and then square root that number gives us 7.7 meters per second. That's the speed that that ball reached. Now, with the information we were given, the height and the mass, that's one route we could have took, the green route, but we were also given a time. So I'm going to call that the red route. So we have a time. The time was 0.8 seconds. We know its initial velocity was 0 meters a second. And we know gravity is pulling it down, which is an acceleration, 9.8 meters per second. And we want to calculate v. That's just the acceleration equation. So a equals v minus u over t. We want to try and find v. So once we rearrange that, if we move t up here, v minus u equals at, v equals u plus at, which is just 0 plus a times t, 9.8 times 0.8 seconds, which gives us 7.7 meters per second again. Two ways you could have done that. Potential to kinetic, or just using the acceleration equation, depending on what you're given in the question. If you're given a height and a mass, then you would need to go the green route there. If you were given a time, you know gravity, as long as you're on Earth, you can do it on any planet. You would just need to change the acceleration from your data sheet. Okay. Right, second last thing is work done. This might be another question that you're given. Work done is force times distance. So we'll put the force of friction as an example there. Force of friction between tires and the tires and the road are naturally going to cause kinetic energy, and that kinetic energy is transferred into heat. That's what wears tires away. There's an example there of a new tire and an old tire that's had a lot of driving on it, a lot of friction, a lot of kinetic energy, a lot of heat transfer. Therefore, the tire starts to wear away. And the equation EW, the work done, force times the distance always in meters. Remember, if it gives you in kilometers, you times by 1,000. Force in newtons, and energy or work done, E, energy is always in joules. Right, final thing, Newton's third law. So Newton's third law states that if an object A exerts a force on object B, then object B will exert an equal and opposite force back onto A. So some examples, rockets, they thrust upward, but the weight acts downward. And when you're sitting on a chair, your weight acts down, but the chair also exerts a force up on you, holding you up. If that force, your weight, was too much, then the chair would break. Another example is if you're in a pushing contest with someone, have you ever noticed when you push someone in that direction, you naturally go backwards? So that's what Newton's third law is all about. You're exerting a force in that direction on person 2 here, and you naturally go back the way in the opposite direction. And another example is, this example is a bit more fun. Two of you on one of these wheelie chairs. You put your feet up on person 2 here and naturally try and push them that way. You will naturally go in that direction. That is because of Newton's third law. Right, I think that about covers it. We'll just go back up to the top, make sure we've hit what we said we were going to. So Newton's first law, we covered that, and I gave you some examples. Newton's second law and some real life examples, we did that. Use the two equations from Newton's second law. That's F equals ma and W equals mg. And solve problems. I gave you one example from that. Solve problems using free fall and work done. EW equals FD, so we did an example of that. And I can state Newton's third law and give real life examples. We also did that. Okay, now you're ready to move on to tutorial questions and then past paper questions. Good luck. Any messages for Miss Murray and I, just let us know and we'll do our best to help you.